Hello, my name is Caroline, and the project I did this semester is called Stupid Assembly. Stupid Assembly is an assembly simulator modeled after an assembly language in a puzzle game called TIS 100. The language in TIS 100 is very simple, but Stupid Assembly is quite a bit closer to real assembly in that it more fully simulates how memory works. Uh, the basic syntax for it is the first word in an operation is a command, and the second or third are locations. The locations being some sort of memory location or something you can read write to. Command can be one of quite a few. They're around 30 or so. It's equivalent to an operator in a higher level language, although it might be a little more flexible than that even. And not all commands require a location, such as like the exit command or return from a subroutine command. Like I said earlier, a location is typically somewhere in memory, or it could also be something that can be read from or written to, such as the standard input or output. And jump commands specifically require a label as a location and not a memory location. The memory structure is composed of registers, a program counter, a call stack, a memory stack, and a big block of memory that you can specify the size of at runtime. Although if you change it during runtime, it'll get reset. SAS has no variables, but pointers can be specified to memory locations, although they're a little tedious to read write from. But to get around that, there are some general purpose registers you can use immediately. Just like real assembly, SAS is typeless, but unlike real assembly, SAS stores everything as a string, whereas in assembly everything's binary, though you can like make it look like other things. This is mostly for my convenience because I don't want to deal with binary, and I do like dealing with like specific bit addressing, but addressing a single character was close enough for me, so that's what I did. Also, it's much like more straightforward to parse double values from strings than it is converting back and forth between binary. The memory locations are as follows. The program counter is an integer that stores the line number of the next instruction in the program. You can't directly write to it or read from it, but if you jump to a label, it will get changed to the line number of that label. The call stack is sort of like the program counter. You can't really directly read or write to it, but anytime you jump to a subroutine, the line number that you were previously on is pushed to the call stack. And anytime you return from a subroutine, it jumps to whatever is on top of the call stack after the call stack is popped. That lets you basically use things as a function or a method. It has a big block of memory as well. It can store any kind of value, and it's basically just a big array of strings that you can read write to. Sorry, memory block is a big array of strings that you can read and write to. And the memory cell that you're reading and writing from is whichever is being pointed to by a special register called the address register. If you want to change memory cell that you're reading and writing to, you have to change the address register. Aside from that, there's a memory stack, which can store any kind of value, but it can only be read from or written to in a first in, last out manner, just like a stack. And it's accessed using the push, pop, and top commands. Those are locations in the syntax structure. The 6 registers Stupid Assembly has are 2 special registers. The first of which is called the accumulator. That's if an operation has any kind of result, it is stored in the accumulator. If you want to store it somewhere else, you have to move it out of the accumulator after the operation into wherever you want to store it. The other special register is the address register. It can only store integer values, and it's intended to specify a memory address that you want to read-write to. The 4 general registers are .A, .B, .C, and .D. They can store anything and can be accessed at any time. Some special locations that the language has are in, which can only be read from, and it causes the program to request input from the user on standard input. The out location can only be written to, and it outputs on the command line. The stem location reads and writes to an address stored in the address register. And different from all the others are pointers, which are indicated by the ampersand in front, and they can only store integer values, and they're intended to store memory addresses so that they essentially function as variables, kind of. They're a little tedious to use, though. To implement the language, I am using JavaCC to parse my instructions. I did not use JavaCC's built-in token manager. I wrote my own because Sass's syntax is very simple, so it was easy for me to tokenize the commands. And I wanted to be able to send the tokens to the parser in any order I wanted, because I needed to be able to arbitrarily jump around in the program and change line numbers, even in ways that don't make sense, just like in assembly. And unlike the calculator example, a stupid assembly is not capable of reading instructions using the prompt. It has to be supplied using a .ass file. The structure of the program is as follows. This is the main class. It's essentially just a wrapper class. It's also in charge of whenever the next line is executed. It's basically just a while loop until it reaches the end of the file, basically. Normally, that's not what happens. Normally, the code will exit the file itself using system.exit command, but that's just to catch an error, basically. There's also this class, which is input-output. It's just a wrapper for Java's functions for that, because I don't like them. This is my .jj file with all of my commands in it. This is the parser itself. Here you can see that I'm specifying my own token manager. I'm not using the main method here, like in the calculator example. Rather, mine is in the Sass class. My commands are down here. These are the locations that I specified earlier. There are sources and destinations. Sources can be read from, destinations can be written to. You can see that in is here, but not here. Out is here, but not here. Sasscore is my token manager, and it's also used to store the memory values like the accumulator, the register. The memory block defaults to 10, but you can set it as any size you want. It also has an array of strings for the code that it passes to the parser in an arbitrary order. The line that is passed next is indicated by the line. It's also the program stack and the memory stack. These are all the commands it has. This is the constructor for it. It just basically preprocesses everything so that it's ready to be executed. And these are just access commands that the parser uses to perform functions. With that, I will get into a demonstration. This over here is a very simple .sass file that simply calculates a factorial of a number that you specify. It also does it recursively using the program stack. And how it goes is it has the move command, which is a command that moves whatever is in the first memory location to the second memory location. You can use a string literal as a source in this case. It basically just moves, enter a number to the standard output, and it'll print whatever is here. And then I'm saying move in .a, which moves whatever the user enters into standard in into the .a register. Then after that, I'm jumping to subroutine, and the subroutine is at label factorial. So it jumps to here immediately and begins executing this instruction, which is another jump immediately to push registers, which pushes all of my memory into the memory stack so that I can retrieve it later. Then once it gets to return, it jumps back to here and continues executing. This is a conditional. It's test equal to, and the n specifies that it's comparing numerically and not as a string. And it's testing if .a is equal to 1. We're going to assume that it's not, so this would be false, and it would skip over this jump instruction. The next instruction is to move .a to .b. It then subtracts 1 from .a. Then this is stored in the accumulator, so it moves the value from the accumulator back to .a. Then it jumps routine to factorial again, and then pushes all of that onto the stack again and subtracts 1 all over again, and it keeps doing that until it gets down to 1. And once that happens, it jumps to exit, and then it moves .a into .d, which at this point .a should be 1, and then it pops the registers and jumps back and continues from here. And then it multiplies .b by .d, which is where the output was stored. So, and then it just continues on like that, collapsing and multiplying things until the factorial is calculated. I can go ahead and execute it. Java sass factorial.sass. I'll try 3. It correctly outputs 6. I'll try a different one. Let's try 10. That's pretty big. I'm going to assume that's right. Let's do 4. 6 times 4 is 24, so that's right. I also did another program, which is quite a bit larger. It's tic-tac-toe. This is about 447 lines, I guess. About a quarter of those are just to print the board to the output. It's ended up being quite complicated to concatenate all of those values onto each other, and there's a lot of reading from memory, which ended up being rather tedious. But I'll go ahead and show that. Java sass tic-tac-toe.sass. It starts off by asking you which row you want to play. I'm going to specify row 1 and column 1. You can see that row 1, column 1 is an X, and the AI randomly chose the middle square. I'll go again. I'll do row 3, column 1. You can tell that the AI is not very intelligent. Now I'll do row 3, column 3, and row 1, column 2, and row 3, row 2, column 2. Oops, row 2, column 3. Whoops. Looks like there's a bug in that it doesn't know how to handle when no one wins or loses. Let's try again. There. That time I won. Let's see if I can make the computer win. This one. There. That is my language. I hope you enjoyed my presentation. Feel free to email me if you have any questions about it, or you'd like the source code or something. Thank you for watching.